Yeah, and then the paper that I picked to present today is called Bayesian sets. It is a paper published in Nips 2006, so 13 years as compared earlier before Thorne's paper.
Still good.
Yeah, but still good. Yeah. Classic one. So the problem of this paper is very simple. Uh, so you have a universe of items, D. So the items could be the web page, a movie, people, word, protein, image. Then the your user provides, or not necessarily the user, the system receives a query, and the query is in the form of a small subset of items of D, like DC includes n different items. That is a subset of the universe that we are considering. So the objective is that we should have an algorithm so that it can provide a completion to the query set, and then that completion should consist of DC and other elements which are also sharing the same concept. So for example, if I put in the query is Putin, Trump, Xi Jinping, right? Xi Jinping, yeah. Then they should return the names of the current leaders. The query set defines some underlying concept, and then you should be able to return other items that also share this concept. Okay, so conceptually it can be illustrated like this, right? You have a universe of items, and then you have a query set. The output, expected output, is a completion of DC, in which DC prime also includes DC plus other items in D, and they should share the same concept. So going to the problem formulation, right? So the idea is simple. Given this query set DC, you should be able to rank all the elements in D by how well they would fit into the set, which includes the query set. Right? Like you should rank how well that into the set of query of current world leaders. And you can do that through this score function. Basically, it's measuring how well the element X, the item X, fit into the query set DC. And it is defined as a ratio between the posterior probability of element X given DC divided by the prior probability of the item X. So this this one is to desensitizing the effect of the length or the magnitude of the vector X.
Mutual information.
Sorry?
Almost a mutual information.
Could you say that again?
It's almost a mutual information. Pointwise mutual.
You mean the PMI?
Yeah.
Could be. So the intuition of this ratio is that it's measuring how different the difference between two hypotheses. The first hypothesis is that the item X and the query set DC come from the same distribution with the same parameters. And another hypothesis is that they belong to two different concepts. So this ratio is basically the difference between the hypothesis that they belong to the same concept or they belong to two independent concepts. So the question now is that how do we compute these quantities, the posterior probability and the prior probability of the item? So it turns out that you can use you can utilize the model-based machine learning, specifically probabilistic model, to quantify these values. So it's assumed that the item is derived from a distribution with the parameter theta, and because they don't know for sure what the value of theta is, so that's why they need to smoothen out the value of theta by defining the probability of theta as well, and then they average out over the possible range of theta. So basically, the prior probability of the item can be defined by this equation. So for the query set, it consists of n different items, right? So it's basically a sum over all the elements inside the set. So given this definition, you can compute the posterior probability of x given dc. So in this formula, there is a term of the probability of theta given dc, which can be computed as in the equation 4. So this framework is very nice in the sense that you can flexibly design the family of distribution so that you can have analytical result to represent this probability of item and the posterior probability. So for example, if you assume that each item is a binary vector, so then and each element in this item follows the Bernoulli distribution, which is this probability, then you can derive the score of the item that belong to the cluster in this analytical form. And one interesting thing is that this formula can be vectorized later if you want to implement vectorization computation, basically to speed up the computing process. Okay, so the math aside, right? The problem we want to do is that given the query set, we want to rank all items in D in terms of how well they fit into the query set. So in this paper, they conduct experiment with 3 datasets. The first dataset is Groliers, which is an encyclopedia. The second dataset is H movie, is a rating dataset, and the third dataset is Nips, is academic papers. So they do all the pre-processing, and then the resulting matrix, which include 0 and non-zero elements in the vectors. So here are some of the statistics of the 3 datasets. So for the Groliers dataset, they conduct some example queries. So given this query set, including Groliers and Soldiers, then the Bayesian sets will return other words which also relate to warrior and soldiers. So this Google sets is used as a benchmarking result. So Google set is actually a product of Google, but it's no longer available. Yeah, at that time I think they have this Google sets when you put in the query in this form of a set of items, then they also return you other related items.
It's not available because of this paper?
Maybe. So then they compare the result returned by Bayesian sets and the Google set. And the reason is that it's hard to quantify the performance of this kind of query because you probably need some people to label that this this result is relevant and that result is not relevant. So they basically use Google set as a benchmarking result to compare the quality of the result.
Then how do they compare the two?
So when you read them, right, you can feel that which model should return a more related, more relevant results. It's not the quantitative, it's more like qualitative evaluation. And they did that for all 3 data sets. Yeah, for the H movie, if the query is Mary Poppins and Toy Story, then I think Bayesian set return other animated movies for children, right? So as some of the movie written by Google sets.
Fast and Furious.
Huh?
Fast and Furious.
Fast and Furious, where? This one?
Fifth, yeah.
Is it the same movie? No, right?
The Fast and the Furious. Is it
The car movie,
Yeah.
the one with the
Yeah.
Vin Diesel.
That's the right?
Huh?
Just Fast and Furious.
No, that is the Fast and Furious.
For Neurips dataset, if the query is Alex Mola, right, and Skolkov, I guess they return maybe co-authors and the topics that these guys are working on. So one interesting application that is not shown in this paper, but it is shown in a later paper, is that you can actually use this Bayesian sets score to measure how representative. Basically, you can find a representative of a set of images. And this example showing that if you are given a set of images labeled cost, right? And after you use a Bayesian score, you pick the top 9, then if the top 9 returned by Bayesian set is a very good representative of the category. And if you pick the top 9 at the bottoms of the ranking list, I don't think it has a sense of cost in the pictures. So, in conclusion, right, this paper provides a probabilistic framework to measure how well an item should fit into a cluster. So if you think about it, we can do many kinds of applications, many types of applications with these Bayesian measures. So you can do anomaly detection. Basically, if the fitting score is not high, then it can be used to detect the anomaly. You can use it to reduce a set, or in other words, it used to select the representatives of the set. Yeah, and then you can also do cluster by concept retrieval. So given a set of items, you can retrieve other items that also have that concept. So